Here we are in exercise 2 of chapter 6, and the goal here is to continue exploring the matrix norm, in particular the Frobenius norm, and write a very simple optimization algorithm. So, in particular, we are focusing on the Frobenius distance between two matrices. Sounds very fancy, but it's actually just the norm of the difference matrix. So the distance, the Frobenius distance between matrix A and B is the Frobenius norm of matrix C, where C is defined as A minus B. So very simple, very straightforward. Okay, so we want to get the Frobenius distance between two matrices to be close to 1. Doesn't have to be exactly 1, but relatively close to 1. And we're going to do this by starting off with two random matrices, 7 by 7 square matrices, and then we create some variable s, that is a scalar. We scalar multiply both matrices, and then basically we want to knock down that scalar until the matrices are closer and closer together. They get close enough to each other that the Frobenius distance between the two matrices is close to 1. Doesn't need to be exactly 1. Okay, so let's see. So we do this in a while loop, and then we report the number of iterations, so the number of times that we multiplied this scalar by 0.9 in order to get the Frobenius distance between these two matrices to be 1. So to start with, I created a function that computes the Frobenius distance between two matrices. So you can see we are inputting matrix 1 and matrix 2. Here is the difference between those matrices, and then this is the Frobenius distance, which is just the distance squared, so all the individual elements squared, and then sum them up and take the square root. Very simple function that is the Euclidean distance or Frobenius distance. Okay, so here's the very simple optimization code. I define two 7 by 7 random numbers matrices. And then here I start with the scalar being set to 1, and then I use a while loop. So I say while the distance between these two matrices is greater than 1, then we knock down the scalar. So we multiply the scalar by 0.9, which means we're just reducing its size by 10%. So it's getting knocked down to 90% of its original value. And we increase this variable, this counter, num iters. Okay, that's simple. And then here at the end, I print out the number of iterations it took. So in this particular run, it took 21 iterations. So S kept getting knocked down over and over and over again. The final value of that scalar ended up being approximately 0.1, and the Euclidean distance was a little bit over 1. Okay, many ways you could set this up. And yeah, there's alternative methods that would have been equally correct. Mainly, the point here is not so much to reproduce exactly this algorithm, but to work with matrix distances and get a very brief introduction to optimization of matrix distances. Notice, by the way, that we're not really changing the information in these matrices. We're not changing individual elements. We're not changing the row space or the column space. All we're doing is globally scaling down these matrices so that the numerical values are smaller so that the distance is closer. Okay, and then just out of curiosity, so here this time it ended up being 21 iterations, and now I'm running it again. Now it's 20 iterations. So this is not part of the exercise, but I was just curious to see what is a typical number of iterations for this particular problem that we were working on. So what I did was basically just take the code from the previous cell. So I take all of this code, embed it in a for loop to run 1,000 times, and I stored the number of iterations for each of those 1,000 times. And then I just create a histogram. So then we see it's pretty stable. So it tends to be around 21, 22 iterations. Sometimes it happened faster. Sometimes it took a little bit longer.